Just some general announcements. First off, we are week 11 currently. So by the end of this week, you should have watched a bunch of stuff on substitution or just substitution. There was a request in office hours to talk through substitution and elimination, so we'll look through see if I can't whirlwind that and keep it relatively short, but you know me. Next week, I appreciate the snicker, is week 12, and then week 13 is our exam. The exam will be on Thursday of week 13, and you might be like, why are we talking about this? Tuesday of that week, I will be out of town, so you'll have a sub that day, which it is what it is. So they'll have access to the practice exam. I might be able to dig up a key for them so they could at least confirm answers within that. Again, I think that's a bad idea, but that's fine. And then Thursday, and then they'll be here for lab too. So yeah, everything should run kind of as normal that week. And then Thursday we'll have the exam. Kind of, sort of? Okay. And since we're looking at the schedule, why not? Then we've got week 14, 15, and 16, which we'll talk about just a little bit right here. 14, 15, and 16 are cram-packed full of content. So if you thought at any point this semester that stuff was jammed in there, it doesn't hold a candle to 14, 15, 16. A lot of stuff is just crammed in there, and in my opinion, that area of OChem is poorly organized. I've tried to do my best spin on it to kind of compartmentalize and package things, but ultimately there's just a lot of reactions there, and I would argue it's a pretty good preview of what you can expect in OChem 2. For my sake, that last 3 weeks effectively gets repeated in the first 4 or 5 weeks of OChem 2, with, of course, new content coming in additionally. But we do try to review that largely because summer destroys any progress we made. So, yay. Yeah, questions about the plan for the rest of the semester? Cool. Then what we'll go ahead, I was trying to find something. So in trying to look through a reaction to discuss our substitution and elimination, I was going to try and find like specific references. It's always nice to have a specific example. So we'll take a look at one sort of from the practice exam. So if we're going to be concerned about what's going on with substitution and elimination, a couple of the first things that you need to kind of reference would just be what's happening within them. So how do you know you've done a substitution reaction? What are you looking for?
Change of an atom, one atom.
Okay. We want the exchange of ultimately one atom. Okay. So real quickly, of course I should color code to make this a little bit better. Have I exchanged one atom in this reaction? Has this one atom moved from the red structure to the orange structure?
Oh, yeah.
So have I exchanged one atom?
Yes.
Yes.
But it's not.
What do you mean, but it's not? What do you mean, but it's not?
Is this an acid-base reaction?
Yeah, this is an acid-base reaction, not a substitution. So I like the explanation of exchange one atom, but we need a little bit more nuance behind it. That one atom can't be hydrogen. Okay. So let's erase all of that. And let's bring in, do you want to bring in? Let's not worry about elimination yet. Let's look at a chemical reaction. Ugh. Keep forgetting I'm on a white background. And I'm going to bring in CH3 chemical reaction. What's my product?
What's your problem?
I've got lots of problems. What's my product? Might be a challenge, right? We talked about exchanging one atom.
Maybe, so you're talking about the arrows put in there?
I'm actually not talking about the arrows necessarily yet. Theoretically, at this point, all we're saying is the definition of a substitution is I exchange one atom. So what would be my one atom exchange?
Bromine and oxygen.
Okay, bromine and oxygen. So if I want to look at the product, we're not doing anything to that ring, so I should just put an oxygen here, and I should put bromine over here. Okay. Is that an exchange of one atom, or have I exchanged an atom from each place? So I would argue in this scenario, what you've done is done a double replacement here, not just a full substitution. Okay? And so this becomes one of the problems in how we would navigate, how we talk through and what these things mean. Our arrows can come into play to help us out a little bit more with this. Because you've got the right kind of bones behind this, but we've got some kind of secondary issues. Okay? Ivan suggested that that bromine should be by itself. Okay? Is that all you want to suggest with it, or do you want to suggest anything else?
The CH3 needs to go with the oxygen.
The CH3 should stay with the oxygen. Okay? But does that fit the pattern of exchanging only one atom?
I mean, yeah, the one atom connected to the CH3 to begin with, wasn't it?
The one atom was connected to the CH3. So the atom that exchanged was the oxygen for the bromine. I don't care what is connected to that oxygen. So I would argue that yes, this still fits in the exchange of one atom. The other pieces were irrelevant to the overall story. The one atom exchange was just oxygen for bromine. Okay? So I lost the bromine and I replaced it with the oxygen. This is still a one atom swap. Okay? Why should I not touch the oxygen to carbon bond? Why should my focus only be on that oxygen and then the carbon to bromine bond?
You said it was only one.
Okay? So looking at our pieces behind it, we might say if I look at that blue structure, the only thing that matters to me really there is that that oxygen is negatively charged. This is a source of electrons. And as a source of electrons, it could donate those electrons to another species. If it donated those electrons to a hydrogen, what did it act as? It acts in an acid-base reaction. That's not what I asked. If oxygen donates its electrons to hydrogen, what did the oxygen act as? Right, that's hard, right? We're having a hard time processing what that is. So let's rephrase that and say, here's a hydrogen. The oxygen donates its electrons to that hydrogen to become this. What did my oxygen act as? It acts as a base because it accepted the hydrogen. And we can see that easier when we look at the product. Some people will look at the product and be, oh, it has a hydrogen. To go back to the oxygen, it's acting as an acid. Yes, look at the directionality of our arrow. Okay. Focus on what we're trying to ask. What is the oxygen acting as on the reactant side? It must share its electrons with the hydrogen, therefore it is acting as a base by accepting them. The accepting appears in the product side. Kind of, sort of? Okay. So it could act as a base. Is it acting as a base in this scenario? Why not?
Because you're not moving around hydrogens.
I accept. Okay. It's not sharing its electrons with a hydrogen. How do we know it's not sharing electrons with a hydrogen? There's no hydrogens around there. There's no hydrogens around there.
They can connect. They are connected to something else.
Even if we set up an acid-base reaction, the hydrogens would still be the same proximity. How do we know it's not sharing its electrons with a hydrogen? Where are you seeing that it's not? You're absolutely 100%. You're like, this is a dumb question. If it is a dumb question, that's fine. I can ask dumb questions.
I mean, you can just see that it's no hydrogen.
Where are you seeing that?
There's no, on the oxygen, I can see there's not connected.
Where? The oxygen shows up twice.
Oh, the product side.
Yes, we look to the product side. When we look at the product side, is the oxygen connected to a hydrogen? No, it's connected to a carbon. Therefore, it did not act as a base because it didn't share its electrons with a hydrogen. It shared them with a carbon. That's fine. Okay, all we're trying to do is subtly nuance based off the clues and the information we have at hand. Okay? So cool. If it didn't share its electrons with a hydrogen, it can't have acted as a quote-unquote base. Then what did it act as? That becomes a hard question. I now need a new name. What do you want to call it? How about Bob?
Is it the electrophile, whatever it is, in either word?
Okay. When we talk through our chemical reactions, we use acids and bases. Acids and bases as terms were defined to explain what chemistry? All chemistry. That was the point of those words. Okay. What we found was that there was other chemistry than just acids and bases. Okay. It started with the Arrhenius definition, H plus and OH minus. Well, there were other things that could accept H plus that weren't OH minus, so Arrhenius definition wasn't accepted. So we shifted to Bronsted-Lowry, and we only talked about the transfer of H plus. They were like, well, dang, the transfer of H plus. There's other chemical reactions that react with things that aren't H plus. So I need another definition. The other definition that moved in was now the Lewis acid-base definition and shifted it to saying, let's stop looking at the atoms moving because the atoms aren't actually causing any chemistry. Okay? I used this analogy in somebody's class. It must have been one of the labs. Okay? If we talk about relationships, that's effectively what's happening here, the relationship between those atoms. Okay? And we could talk about marriage. Well, what is marriage? Is marriage the proximity of people next to each other? If that's the case, am I now married to Josie? Sorry. She figured, no, he's not. Okay? No, proximity doesn't change things. There's something else that has to change to allow a chemical reaction. What's that something else? It's not proximity, it's
Connection?
what's the connection?
Bond. Marriage? Or
What's a bond?
love?
I understand this. Electrons. So our focus becomes on electrons. So Lewis brilliantly looked at it and was like, I don't care about atom locations, I care about where the electrons are located. This is why we created Lewis theory in structures so that we could explain where the electrons were located in a molecule. Because once you knew that, you can then explain how the electrons could move between different places. And once we start talking about how electrons move between different molecules, what have we now just defined? Organic chemistry. Right? And if we look at the history of chemistry, we're looking at probably thousands of years. Organic chemistry really came into full kind of force starting 1900. Okay? There are a couple people that discovered things earlier on, and we'll name them for stupid reasons later on in the semester. Okay? Give them a little bit of credit where credit's due, but they were ultimately just kind of mismashing things and didn't quite understand what was going on. The theory behind how we build things and put them together really only came into kind of full birth early 1900s. We got a delay there because then we started talking about nuclear chemistry, but then we move into full kind of organic chemistry probably through the 30s through the 60s, 70s. Right? There was a big resurgence in OChem in 60s and 70s. Anybody know why?
60s and 70s? Medicine.
Yeah, medicine. That's what we call it.
Drugs.
Drugs. Okay, that's the nice way of saying it. Yeah, medicines, drugs, like LSD. Yeah. That's where organic chemistry had a huge spike in popularity because people were like, oh, I could make something to play with my brain chemistry. Okay? Talk to old organic chemists, you'll understand. I'm not that old. Okay? So we're looking at a relatively new kind of development, and a lot of that came from recognizing the electrons, and now how do we define them? Well, as brilliant as Lewis was with coming up with this definition of sharing electrons, it now became too broad. Because I could call this a Lewis base. Is that a base donating electrons to hydrogen, or is that doing something else? If I just call it a Lewis base, I don't know. Now I've got this whole open world of things I can apply to, which is why I don't like using the Lewis definition for acids and bases. And when I talk about acids and bases, I'm very specifically talking about Bronsted-Lowry acids and bases, because that narrows the field of chemistry. That when I talk about an acid, I'm talking about an acid-base chemical reaction. So how do I change my language? If I can't talk about this ability to donate electrons with that, I'm not getting rid of that. I'm getting rid of the term we use to explain it. In this case, I want to talk about this sharing electrons with that positively charged thing. Why is that carbon positively charged? You're like, but it's not positive. Fair. Is it partially positive? Yeah, why?
Because the pole of the bromine is pulling the electrons towards it.
Why does bromine pull? What is it pulling with?
It has a higher electronegativity.
It has a higher electronegativity. So if I have this concept of electronegativity, that was the response I was going for. Okay. I can now predict some of that polarity and some of that chemistry associated with it. That bromine being partially negative, I'm going to flip that color, and that carbon being partially positive, I could expect these electrons to share to that carbon. Okay? That's predicting what I'm expecting in the product. The negative goes to the positive. If I can find those negatives and positives, I've got a good step up on how I should predict this. But now it's sharing electrons. Yes, that's the base, but it's not sharing them with hydrogen. That's where I introduce, or where we introduce, a new term. That new term, as Adolfo was referencing in this particular case, is calling it a nucleophile. Okay? Why nucleophile? Well, it's sharing it with a positive. Where are the positives found? In the what? In a nucleus. So if I'm talking about a nucleophile, I'm talking about something that is attracted to nuclei, quote unquote, and the nuclei is positively charged. Really what we're just saying is that this is a positive loving atom. It is positively loving because it is unstable. Why is it unstable? It's negatively charged. So if I can piece together those aspects, I can now start to predict some of their chemistry. Right? If that was all that had happened, the oxygen sharing its electrons with that carbon, we'd encounter an issue. What would that issue be? An octet issue. We would have exceeded the octet because there's an implied hydrogen. So not only did that oxygen have to share electrons in, but I also had to do something else.
Take electrons out.
I had to have that bromine take electrons. Why did the bromine do it and not any of the other atoms connected to the carbon? The bromine being more electronegative. That's why it was important to identify the polarity of that bond. Okay? That is why it's important to be able to look at a bond and say that's a polar covalent bond versus a non-polar covalent bond, because that allows me to predict something about their individual chemistries. This is why we address that in Unit 1.
So we now have those tools to use here. Okay? What's the result? Well, do I have the CH3 floating off on its own? No, I didn't touch it. All I touched was a lone pair of electrons on that oxygen and turned it into a bond, which means the CH3 is still connected. So I can delete that one. What happened to the bromine? It has that lone pair now that it has gained from the bond, and therefore should be negatively charged. If we look at the balance of this chemical reaction, we overall started with a negative charge, which means we should overall end with a negative charge. So everything has now worked its way out. What we've now done is a substitution reaction, and on top of which, we've now layered more information into it. We said how it happened. How did we say how it happened? That's what those curved arrows meant. Okay? There were two arrows describing how the substitution reaction happened. Okay? In this particular scenario, we weren't concerned necessarily about when it happened. We just said that how it happened, or that it happened. Which brings in the next part of looking at a substitution reaction. The substitution reaction isn't just that it has happened, it is both how and when. What do we mean by that? Well, there's two arrows here. These curved arrows are the how. When did they happen?
Immediately.
Okay? If they happen all at once, I could call that a particular type of mechanism. Okay? So it would be a substitution reaction beginning to end, but now if I say the how that substitution reaction happened was everything happened at once, I can call that a name. Okay? That name I want to call it, there's a couple terms that could come out. We'll sometimes get immediate. We'll hear simultaneous. Concerted doesn't show up quite as often when we're talking about this particular mechanism, but you could see concerted. Okay. Well, what happened? Beginning to end, it was a substitution. Yes, substitution. How did the substitution happen? Well, a nucleophile had to come in and attack. So we could call it an SN, because the nucleophile is what drove this reaction. Okay? And now we run into, well, why don't I just leave it at that? We just call it substitution nucleophile. Okay? Well, the substitution nucleophile, the next part of that comes into play because we discovered there's multiple ways that these two things can happen. And because there's multiple ways they can happen, we have to name them differently. Okay? Anybody have siblings? Like lots of siblings? Anybody? Yeah?
Two brothers.
Two brothers? Are you oldest, youngest?
Youngest.
You're youngest? Have you ever been called number 3?
Yeah.
Yeah, see, there you go. Okay? I was number 3 too. Okay? 5 brothers, or 4 brothers, 5 boys. Okay? And we were 1, 2, 3, 4, 5. Okay, why would you use 1, 2, 3, 4, 5?
Easier.
It's easier. Instead of memorizing some arbitrary name associated, we could just number them and say, that's 1, that's 2, that's 3. Okay? It may sound like a silly naming system, but that's how a lot of things are named in biology. In chemistry, we actually have a reasoning behind why we number things. Okay? It's not just arbitrary. Okay? In this particular case, we call this SN2. But this was the first one we looked at. Why don't we call it SN1?
Because there's 2 reactions going on at once, or
Why do we call it 1 versus 2? And that becomes a harder statement to kind of pull out. That comes into looking at the details of how these reactions work. Right? So if we were now going to look at how these reactions work, what we might need to do would be pull out our 152 knowledge, and what we studied in 152 was we looked at reactants and products and how we transition from reactants to products. We quantified the hell out of that, but ultimately what we were trying to say is that we could end up with something that looked like this. we have a reaction coordinate, and we have an energy diagram. Reactants go to products. Okay? We also have this activation barrier that prevents the reaction from going. That's our EA. That first part, our EA, is all about the kinetics. Everybody loved the kinetic chapter. Don't worry, you're not alone. And if we just looked at the reactants to the products, that's just looking at the energy difference between those. We're now talking about thermodynamics. Depending on what we are concerned about, we will look at either one of those. When we look at our overall reactions in this semester, for the most part, we ignore kinetic versus thermodynamic. Okay? And we don't have to stress about it. Second semester, it makes a really big deal, and we have to have conversations about kinetic and thermodynamic. We'll talk about it a little bit this semester, but not too much. I just want you to be aware it's there. Why does this become important to us? This name is trying to pull as much information into it as humanly possible. It's not that it was discovered first or second, biology. Okay? It's now referencing something about its inherent chemistry associated with it. Okay? Well, the mechanisms gives us some information behind it. Okay? Is that a particularly chemically useful reaction? What would make something useful?
As far as useful to us, as humans?
Yeah, for a useful chemical reaction. You're a chemist. What's the point of your chemistry?
Drugs.
What about the drugs?
Make it like
I want to make drugs. Okay, so I start with not drugs, and I end with
drugs.
drugs. Okay. Is that all you care about?
This is going to sound great in the recording, I'm
The
sure.
product, the amounts.
How much product do I get out? What's going to dictate how much I get out? And that framing is a little weird with that wordage, so I don't think I want to report that. Okay, but how many reactants you put in, okay, is sort of, but that's just saying I have tons of money and I just throw reactants at this.
How much reaction reacted?
Okay, how likely it was to succeed, right? How do we quantify how likely a reaction is to succeed? Said another way, not drugs, drugs. Not drugs, drugs. Which of these two pathways, we'll call them A or B, is better?
B.
Why is B better? Quantity. That's an interesting statement. What are you assuming is on this y-axis?
Electronegativity? Or reactivity?
Amount.
Amount. What did I say was on the axis?
Oh, shit.
Energy. Is it going to be easy to get my drugs if they're higher in energy than my not drugs? No, in fact, that's a crap reaction to run. The odds that I'm actually going to successfully make them is very slim to none. Okay? I want a system where my drugs are lower in energy than my reactants because then I can increase the yield of my reactants. Okay? Without having to play nasty equilibrium games. Okay? So we could look at that. Okay? Is it an exothermic reaction? Ooh, if I got an exothermic reaction, I could potentially
Yes.
produce more drugs. Cool. Is that the only thing that matters?
Yeah.
I mean,
Yeah? Cool. Okay. When in doubt, let's always go through another reaction. So here we go. Not drugs, right? And drugs. Oh, let's go all the way down here. Drugs. Okay. Which one of these do you like better, A or B? Assuming you were trying to make drugs.
What's the activation
Is it just the difference in energy between the reactants and products that matters? No, because as you just pointed out, what if that's my energy diagram? Ooh, now I don't want to do B. Okay? It may be energetically favorable, but the activation energy is through the roof. What does that mean happens to the rate of that chemical reaction?
longer?
It takes longer. So this one may not yield me as much, but I can get it in, I don't know, let's pick a day, random unit. This one, I get a whole lot more, but I got to wait, I don't know, 20 days. Okay? That's not going to have the same effect. So when we're going through and looking at our chemical reactions, we want to be thinking about this thermodynamic and kinetic aspect. And in particular, if we go back to our chemical reaction, and I now want to say something about how we run these reactions, kinetically, how would I describe the rate for this chemical reaction? Well, I don't have an energy diagram. Do you need an energy diagram to explain rate for a chemical reaction? You're like, I don't remember. This is where you're going to rely on somebody else who took 152, hopefully in the most recent semester, to be able to explain to me what the rate is for this chemical reaction. You can look at pKa's. pKa's, K stands for, K stands for equilibrium constant. When we're looking at a pKa, we're looking at equilibrium, and equilibrium is dictating based off of the energy of our reactants and products, which means the thermodynamics, which means pKa ultimately isn't going to be useful to us. How do we define the rate for our chemical reaction?
Did you multiply the concentrations?
Isn't that what you did with K?
Is that for
Oh, I don't remember any of these things. I know. I thought this was Zochem, not freaking 152. Say it again.
Concentration of the products over reactants, or the other way around?
I can't say the other way around, but the concentration of products over reactants is a lovely answer to the K equilibrium statement. How do we define our rate?
It's like K times the reactants, I think.
K? I thought we said K was equilibrium. No, own it. Own it. You got it.
Just K.
What K?
The K or just that K.
What K is this in comparison to the pKa?
Oh, right.
Lowercase versus capital K. Capital K was equilibrium. Lowercase k was our rate constant for an individual chemical reaction. That rate constant is what incorporated all that activation energy and alignment and all that nasty stuff that we remember all the way back in 152. That, ultimately a minor point. What did you say after our rate constant K?
I'm going to change it to multiply into the concentration
Of?
the reactant, like K.
Of the reactants. How many reactants do we have in this reaction? We have two.
What are my two?
We have the alkyl halide and we have the ethoxide. Those are both reactants. Okay? Well, but if we remember rate constants were only dictated based off the slow step in the mechanism. So Mike, hold your horses. We got to make sure that we're looking at the slow step. How many steps are there in this mechanism? One, which means by definition,
That is the rate defined.
this is the rate defining step. Okay? I did hear a 2 come out. There are 2 curved arrows. How many mechanistic steps are there? 1, that's the big arrow. The curved arrows is all the stuff happening in that one mechanistic step. Okay? When we talked about those reactants, how many reactants did you say there were?
2.
How many reactants did you say there were? 2. Why do we call it SN2? There are 2 reactants, not just 2 reactants. There's 2 reactants when and where?
On the
In the rate determining step. That's where it's all coming from. Right? So that if we said SN1, what would that then mean? There's 1 reactant, when and where, in the rate determining step. So we would have to go through and look at the mechanism to dictate what's going on behind it. All we kind of stumbled through was just what had to happen, generally speaking, what's going on, and because of how we reflexed into drawing this, we naturally drew this out. That was it. Okay? All these other things come as natural repercussions of that action. Okay? Which is an interesting thing to learn. Everything you do is either intent-wise or non-intent. If you don't have an intent, the decision's being made for you. Okay? Think through your exam. If you don't bubble in a Scantron exam, okay, because you didn't intend to fill it in, whose intent is now taking over? Mine. You've removed your right to intent. That sucks. I would argue that sucks.
So you just keep going up like SN3, SN4.
So is there a limit on the possible mechanisms that we could get out of this? Well, to address that, we have to say what happened. Okay? So let's go back to this and say this is what happened. So let's take a big, giant leap backwards, okay? Which is good. It is good because that sounds kind of bad. It's good to leap backwards.
Yeah, it's cool. I'm done.
Okay? Let's go all the way back to this and say, well, what happened? Okay? And in particular, how did this happen? Well, the what, there were two things, right? I'm going to use alpha and beta as my numbering system for these two things. Okay? How could those two things happen? We just addressed one. Okay? And we called that 2. We said alpha and beta simultaneously, right?
Yeah.
Well, how else could this happen? If you want a hint, how else could this happen?
The beta first, and then the other one.
Beta, then alpha.
And 3 would be the alpha, and then beta.
Alpha, then beta. Good. Thank you for paying attention to that, if you were paying attention to that. Otherwise, good job looking into it. Okay? Cool. So there's 3 ways, which means if we were going to look at a substitution reaction on how it happened, there's going to be 3 mechanisms, SN1, SN2, SN3. Do I have any more options? There are only 2 things that happened. I would have to fundamentally alter how this reaction happened. Okay? Instead of moving pairs of electrons, maybe I moved single electrons. That's going to change a whole new dynamic behind this. Okay? On top of which, does it make sense to move single electrons? Why is this oxygen reactive? What makes it that charge?
Electrons.
The extra pair of electrons. So to fix that charge, I want to move a pair of electrons. As soon as you see charge, you're going to be running in pairs of electrons. So there's really only 3 ways we could possibly output this. Okay? Cool. So I only have to deal with 3 possible ways. Wrong. I don't have to deal with 3 possible ways. Let's take a look at 3. Is 3 possible? What would it mean? What would my reaction look like if I did alpha, then beta?
It would fill the octet of the carbon. It would try and force its way.
Come on. Alpha, form the bond. What's the product? Okay, and you're going to have to help me, Ivan, because I'm looking at this and I don't see an issue.
Well, there's an implied hydrogen.
Like
Remember there was an implied hydrogen back there? We didn't show anything happen to it, which means it is still present, which means if we look at our result of this mechanistic step, we have an exceeded octet. Am I allowed to form an exceeded octet? No, which means this structure is invalid. If this structure is invalid, can I do this arrow? By itself, at least. No. Which then means
So 3's out.
3 is out. I don't have to worry about 3. Yay! Life got better. Less work to worry about. Okay? Well, then what's the other option?
B then.
What was the issue with B? Or how does B work? Walk me through it.
I mean, it kind of leaves the whatever that's all by itself. Yeah. And
Okay. you've got enough words that I can work with that. What we do is add our curved arrow into that. The bromine leaves. The electrons go with the why does the bromine take the electrons? Bromine is more electronegative than the carbon, which helps me to predict some of this chemistry. So I would get this structure. I'd get my bromine chilling out here with that extra pair of electrons. And then I'd get this structure, my OCH3 still chilling out here, right?
Yeah.
Did I do it all correct?
The charges.
No, I'm a failure. Ooh, good catch. There's a charge on the carbon. That carbon just lost electrons. It is therefore positively charged. That's the hard one to catch. The easy one,
Bromine.
the bromine, is negatively charged. Okay, that's what it means to do beta first. Okay, now what happens?
Now it attaches.
Alpha comes in. We now form the new bond between our oxygen and our carbon. We get the Br minus if we just carry that through all the way. If we look beginning to end, is it the same thing that happened up here? I think I deleted the bromine somehow. Yeah, it's the exact same thing. So there really isn't any difference in this. It's just a question of how. Okay? Well, does that how change anything about our rate? This should become a vastly more complicated question, because in this particular mechanism, which is my rate determining step? Why is that harder? What's that? There's more steps. I can't just be like it's the only step. That's the one. Okay, well, how do I decide my rate determining step? That rate determining step has a lot to do with what's easier to navigate. I'm going from a neutral organic molecule here to one missing its octet. Is that easy or hard? That's hard. Okay, you're making a structure missing its octet. That's very high energy. We're not looking at a happy state. That step is very challenging to pull off. How about the next step? Why is it easy?
I mean, I think it's easier.
Why?
Because it's positive and negative trap.
Which does what to their charge?
Neutralizing.
Yeah, neutralizing the charge. So if we were to take a swing at it, the second step is irrelevant, and the first step is our rate determining step. Why does this become important for us? Well, the whole point of our conversation when naming out these individual mechanisms was to do what? Look at our rate law. How fast do these reactions happen? And so for this new reaction that I've drawn out down here, I can say the rate is going to be equal to rate constant. The rate constant is going to be different because it's a different mechanism, times what? The concentration of our reactants in the rate determining step. So let's go through and look at the rate determining step. How many reactants do I have? It was like 2. Really? Did that do anything? No. Is it a reactant if it doesn't do anything? No. How many reactants do I have? I have 1. It's just the organic halide. If I only have 1 reactant, what am I going to name this mechanism? This one gets called an SN1 mechanism. The one shown above gets called an SN2. Everything that we discuss about differentiating these two mechanisms away from each other has to do with looking deeply at each of those individual mechanistic steps and trying to process what those things mean to us. Okay? So we have to identify every single species and say, why is that important? Would that thing have an effect on my overall reaction? Well, I don't know. Let's look at it. So let's try it. That's not quite what I meant to do. That's what I meant to do. Painfully, slowly erase everything. And we'll address this question in a second. Why am I putting SN2 first?
So that I know.
Why not put SN1 first? I mean, it's 1 versus 2, right?
I mean, I feel like if you're asking me a question like, hey, I want you to do it this way.
Why would I want you to do it that way?
Because smart word wants one answer. I don't know.
It's not a bad idea, but no. So we're to draw out all our individual pieces. The bromine takes our electrons. So let's walk through probably the biggest difference between these. If we were to look at the rate laws, which you guys should have because you're all taking notes, not to throw any shade. Keep recording, please. The rate for the top one, say, is K, and I'm just going to, because I don't want to draw the structures again, 1 and 2. Everybody okay with that?
Yeah.
The rate for the bottom one, we'll just say is K times 1. Everybody good with that? Okay, maybe I need to do a label. 1, 2. 1, 2. Let's shift to one of the biggest things that can dictate these. In this chemical reaction, because it's the same chemical reaction in both, where should our primary focus have gone to?
Oxygen.
Why the oxygen?
It's got all the electrons. It's got the charge.
Thank you. I wanted the charge. Okay? The oxygen with a negative charge was our biggest signifier for chemical reactivity, so we wanted to focus on that negative oxygen. That negative oxygen, as we went through and dictated, came out to be a nucleophile. And when I'm going to go through and look at these individual reactions, if I can change the nucleophile characteristics, does that change my overall reaction? Okay? Well, let's think through it. Your original answer was just the nucleophile had all the electrons, and I paused a little bit and you said negative charge. Does a nucleophile have to have a negative charge? What must the nucleophile do?
Still need electrons?
Does it have to be negatively charged? No, it just has to have electrons. Okay? So what is the difference between, say, a negative nucleophile, lone pair, and a neutral lone pair?
It'll be more stable if it loses the charge.
Ah, so one without a charge would be more stable. One with a charge would be less stable. We talked through those charges dealing with stabilities. Awesome. Okay, why does that matter? Okay, well, now what we could go through and do is we can spin this a little bit, and we could reference the negative one being more unstable, more reactive, and we could call it strong. And we could call the neutral one weak. Well, for the substitution reaction, does it matter which nucleophile we use, be it strong or weak?
I mean, preferred.
Prefer what?
I prefer the strong one. 'Cause
Why do you prefer a strong nucleophile?
it's more likely to happen. You wouldn't have any, like, not neutral.
More likely to happen, right?
Yeah.
Okay. I'll go with you. I like that story. Okay? Survival of the fittest. Let's take a look at the SN1 mechanism. Let's take a look at our rate. What dictates the speed of this chemical reaction?
The one.
Structure 1. Is that my nucleophile? What happens if I change the strength of my nucleophile? Is that going to change the speed of my chemical reaction? No. Do I care about the strength of the nucleophile when looking at an SN1 mechanism? No. But what if I switch to an SN2? If I use a strong nucleophile, it's going to react faster because the nucleophile contributes to the rate. Interesting. What does this mean for us? What this means is if I suspect I have an SN2 mechanism, what I can do is look at the nucleophile. Is it strong? That's likely an SN2 mechanism. If I look at the nucleophile and it's weak, that suggests an SN1 mechanism. So a very quick read of the reagents given to me allows me to quickly shift between one mechanism versus another. That's pretty cool. All I got to do is look for a charge and it changes the mechanism. Yeah. Why does that matter? Why does it matter which mechanism works? That's a really hard question, for the record.
More likely to happen?
More likely to happen? Not really, because all of that's going to be largely dictated in our rate constant, which is looking at our activation energy, which is beyond the stability of any of those individual pieces, so we really don't get a window at that. Why do I care which mechanism happens?
To speed up the reaction.
Okay? If I know which mechanism it is, I could potentially speed up the reaction. Okay? I could add a whole ton of reactants. And if it was SN1, the whole ton of reactants I add is the alkyl halide, not the nucleophile, because the nucleophile is not going to have an effect. Okay? So it could allow me to change the speed of my reaction. Okay? Ready for a fun one? The structures that I picked up here for our starting materials, relatively benign. Okay? But let's go ahead and make it a little bit trickier. So here's the subtle change. You ready? I didn't even ask. Why? What's problematic with that?
I think that's usually indicative of something to do with chirality, and that disgusts me.
Ah, indicative of something to do with chirality. Okay? Yes. Chirality is now going to come into play. Okay? And to really kind of make this a little bit clearer, we would also technically need to change our bromine. Okay? Why is this going to matter? So if you note, I added the methyl the same in all three cases, right? Or all my cases. The bromine I only changed on the starting material, but I did not define the bond with the oxygen, that new bond that came in. Why did I not define it? Cop-out answer, because I want you to tell me what the answer is. All right, so which one do you want to look at? SN1 or SN2?
It's easier.
I think SN2. Let's do SN2. Okay. SN2 is a little bit easier because it's one step. It's all happening at once, right? Okay. What should that bond to the oxygen be? Should that be wedged or should it be dashed?
On the product side?
Hmm?
It should be wedged.
Why?
Because it was wedged to begin with, so I'm assuming it's kind of, in my head, like in 3D, like I'm imagining everything's already pushing it, creating like a space for it, so it's pulling out.
I love what you're using there. In my head, I'm imagining the space for it and what's going on with it. Okay, let's work through that. The wedge on the bromine is what? What does that line represent? What does that wedge represent? What's coming at me? What's the bond? You said it earlier. What's the bond? Bullshit. Electrons. There are electrons coming at you. Why is that important? What is the oxygen bringing in? Electrons. Can I put those electrons in the same space where two other electrons are located?
No.
No. I'm only allowed 2 electrons per any individual orbital, which means I cannot place those electrons into that exact same space. If I can't place them in the exact same space, where must I place them? The other space. You mean the exact opposite space of where that wedge is. What's the exact opposite of where that wedge is? A dash. Due to that electron-electron repulsion, which, by the way, is a half-assed answer, okay, we cannot have our nucleophile come into the exact same space that our bromine or our leaving group is leaving from, because that puts too many electrons in the exact same space. What does that mean? If I start with a bromine that is wedged, my nucleophile is going to come in dashed. What happens to the other chiral center? Good answer. Nothing happens to it. Okay? Nothing at all, because I didn't do any chemistry there. Well, why did you show it? I had to show it so that we had a chiral molecule. If I didn't put it on there, it was achiral, and all of this was a moot point. Okay? Kind of, sort of?
Mm-hmm.
Now what happens with SN1?
Now I feel like it is kind of the same thing, except it replaces the spot that was already available. Like, kind of the first time,
So now I want to talk about where the oxygen goes. The oxygen is going to go to the carbon, right? So we're talking about that previous step, okay, our initial step. That negative oxygen is sharing with that positive carbon. Okay? Should it be wedged or dashed?
I'm going to say wedged.
No. Someone suggesting that the answers I provided might have been misleading. Yeah, it's both. The result that we get out of the second one is that I get this product and I get this product.
Isn't there a better answer though? Like hey, like the electron is closer in this end. So
Technically, there is a better answer that you don't want to get into. But if you really want to ask that, you can ask after class. Okay? Why is it and? The other one was singular. It wasn't even an or. I had to be dashed. This one's an and.
It's got two places to choose from. Now that we went in one step, it pulled it out. Versus the other one happened at the same time.
What's the space it's reacting with? What is the oxygen donating electrons to?
Carbon.
Be more specific than carbon. Be more specific than a positive. Getting to the right direction. The positive is not in an sp2 orbital. The positive, by definition, is missing electrons. It doesn't have electrons. So the hybridization of that carbon is absolutely sp2 because it has 3 groups of electrons. And if you're wondering about the third, remember our implied hydrogen. Which means in our hybridization, the sp2, those 3 orbitals, all have electrons in them. Those are the bonds. Why do I have a positive? What's left if I take S and 2 p's? A p orbital. Where's that p orbital located? It's located at that carbon, but where? If I were to draw it, where would it be? You're like, I don't remember all that from Unit 1, where we were told that we should pay attention to our molecular orbitals and our atomic orbitals so that we could understand what would potentially happen in said future. That future has arrived. That p orbital must be perpendicular to the bonds. The bonds are all in the plane of the molecule, which means that p orbital is coming in and out of the plane at us. If I were to take that carbocation structure and turn it a little bit on its side, I would see the p orbital here. Why has that become important? Where can I place that lone pair of electrons? I can place it on top or the bottom. And I'm now looking at random chance of which one happens to align with that oxygen, which means the output is both. Why has that become a big deal? I said we should draw the SN2 over the SN1. When you go through and build your drugs, okay, and you're going to try and make said drugs, in the process of making one of those drugs, are you trying to make a whole bunch of different versions that aren't said drug, or do you want only that drug?
Only that drug.
Only that drug. And that all has to do with chirality. Why does it have to do with chirality? Because our bodies are chiral, and if your drug doesn't mirror the potential chirality systems, instead of making good drug, you could be making very, very bad drug, and not in a good, bad way, as in a bad, bad way. Right? So when we go through and look at organic synthesis, we tend to preference the SN2, because when I go through and run an SN2 reaction, how many products do I get? One. And SN1 gets me 2 products. That muddies the water. Okay? And we don't like muddy water. Yay. Kind of, sort of?
Test me on it.
Okay. All of that is coming out of content that we've already discussed and very painfully, slowly worked our way through so that we could look at each and every single one of those stages. Nothing that is up on that board, I would argue, is new. All it is an application of everything you have talked about to this date within your chemistry career. This is one of the reasons why OChem is incredibly easy and incredibly hard, because we don't acknowledge the amount of backward content that we had to know. And so we tried to memorize our way out, and it comes back and haunts us, and now we have to memorize even more. Okay? What we have just addressed is two pieces of our SN or of our substitution, our SN1 and our SN2. We've got two different mechanisms. We address the strength of the nucleophile, and we address why we care SN1 versus SN2. Because it changes out the amount of products that we get out of it. All of those products go back to molecular orbitals and all sorts of fun, nasty stuff like that. Believe it or not, the SN2 really does go all the way back to molecular orbitals. And if you don't believe me, rewatch the lectures, because I actually told you that back when we talked about molecular orbitals. We use the exact scenario for the SN2 to dictate why we get what's known as a backside attack. Okay? So when you look through our substitution reactions, what you're going to see more often than not, let's see if I can do this without my computer shutting down.
Is that what you meant when you said backside attack on like your videos?
That is it. That is it. Not some sinister other thing. When we look at our reactivity of our alkyl halides, when we're talking about substitution, you see all these pieces? We have to address what our substrate means, what our nucleophile means, what our solvent means, what are the complications that come out of it. So this one's actually not the best summary of it, right? Because I think I broke it into two slides if I look at this. I think the next slide, yeah, brings in the complications thereof. Okay? So all of those things stack. Okay? How do you want to navigate that? I've been trying to set you up with that 95% confidence level so that you know the content so you can just apply it. Okay? That's not easy. I fully understand and appreciate that. But that's what I've been setting you up for. If you choose to not do that, what you're instead doing is memorizing a table like this, where it now spits out all of the individual outcomes that you need to be thinking about. So when you look at the substrate, what substrate do you need? Okay. Well, primary concerns, steric hindrance, that one's a little bit of a hard term at this point. I'll address it in a second. Or cation stability. Why do I care about cation stability in the SN1 versus the SN2? Well, when we drew it out, where did you see the carbocation? In one of the structures. We saw it only in the SN1 mechanism. I don't care about carbocation stability for the SN2 because there's no carbocation. Okay? What does that mean, carbocation stability? Well, do you know anything about cation stability? If you're like, no, I don't remember anything about cation stability. Right? Well, there's two outcomes. One, you either memorize it or we draw a carbocation and say what would dictate why a carbon would be more stable than another carbon. How could I stabilize that carbon? What makes it unstable? What charge? How do I make a positive charge more stable? Give it more electrons. You mean if I put 3 carbons around that, that's going to be better than if I put 3 hydrogens around it? Yeah, it would be, because those carbons have more electrons. What we're discussing there is tertiary is better than, in this case, zeroary. Where did you learn that?
Your videos?
Which videos?
The first one?
Nope.
This week?
That was first addressed when we talked about mass spectroscopy, where mass spectroscopy was all about Stability of carbocations. Trying to lay those seeds so that you've got that content to build on. Okay? You could also look down here. Tertiary is better than secondary. Why does it not list primary or zeroary? Because those don't react in SN1. So you can use this table to memorize your way out. Okay? It still requires a significant amount of interpretation. Okay? So I put this table generally at the end of the slide deck, not at the beginning, because you still have to deal with a lot of interpretation. We asked about some substitution stuff. Here you go. These are all the pieces that you need to pick up out of it. Okay? That's for substitution. Okay? The question that was actually initially asked was, I want to hear about substitution and elimination. Guess what? Elimination does the exact same setup. Why would elimination get me the exact same system? What's an elimination reaction?
Eliminating an atom or a bond.
And because you said eliminating, that's what I wrote. An elimination. Okay? Sort of eliminating an atom, but how is that different from substitution? Didn't you eliminate the bromine?
Yes, but we replaced it. Yeah.
What's that? Okay. So you don't put anything in place of it in an elimination? So you should end with a charge structure? No? What's an elimination?
Stable pi bond.
Okay. You're looking at the formation of a stable pi bond. So if I were to go through and look at that structure that we started with our OCH3, what did we say that OCH3 could act as with that lone pair of electrons? I could have it act as a base and remove that hydrogen. That hydrogen could swing in to form a pi bond. That would be a problem because what would happen at my next carbon? Break an octet. So what must I do?
Move it again. Resonance.
Eject the bromine. What's the result?
Bromine floating around.
I get bromine floating around. What was one of the byproducts in our substitution reaction? Bromide floating around. Yeah. Okay. And I would get my OCH3 now with a new bond to a hydrogen. How is this reaction different than what we just looked at? Or really, how is it the same?
Same stuff.
Exact same starting materials, exact same leaving group process. What's different is how we stabilize that partial positive charge on our carbon. Is it stabilized by a direct substitution, or is it stabilized via an indirect acid-base reaction? In dealing with that indirect acid-base, that hydrogen is being removed from a very particular spot. Said another way, the hydrogen out here cannot be removed. Doesn't work. The hydrogen that must be removed is often referred to as the beta position, because if I look where the leaving group is located, the leaving group is located at my alpha carbon. The hydrogen would be located at a carbon next door. So I will call that my beta hydrogen. And when we talk about our eliminations, you will often hear reference to beta eliminations, as in you are removing or eliminating a hydrogen from our structure, which then goes to make a pi bond, which then ejects out our leaving group. So we end up using almost all of the same terminology that we use within substitution. Note, we still have arrows. All of those arrows now go through the exact same logic system that we used with our substitution. What happens first? Okay? When do those things happen? If they all happen at once, what kind of mechanism do you think you have? Simultaneous. Awesome. Could I call it an S mechanism? What did the S stand for in our S mechanism? Substitution, except this one is now elimination. So I might call this one E. Okay? Should I use the word N? What did N stand for? Nucleophile. Am I using a nucleophile? Okay? It's the exact same structure. Why can't I call it a nucleophile? What is it sharing its electrons with? Hydrogen. It's not acting as a nucleophile. It's acting as a base. It's removing a hydrogen. So we don't use the N terminology. We could then look at the rate. If this all happened at once, how many reactants do I have?
One.
Don't look at me, look at the screen. How many reactants do you have if this all happens at once? Two. So we would call this E2. How could this be made slightly more useful and not like a sudden shock? Was an E2 mechanism something that you were told to process? Stupid computer. Why did it even do that? My computer's still on. That's apparently because I should stop talking. The E2 mechanism was summarized in Chapter 7 when we talk about all of our mechanistic steps, and you should be familiar with what they are so that when they appear and we start talking about the details, you aren't surprised or blindsided by the mechanism. You can now start looking at the pieces behind said mechanism. Hooray! 3 weeks, 2 weeks, 2 weeks. If you count this week, 2.5. Ivan, what question in the homework do you have?
Question 7, chapter 7.
One of 4 steps in electrophile aromatic substitution reaction. For the record, the electrophile aromatic substitution reaction is a complex mechanism that is typically talked about in second semester OChem. We don't care about the understanding this mechanism. What we care about is drawing the products of said mechanism. I'm trying to zoom in, it doesn't look like I zoomed in enough. Okay, so what we want to describe is how does this chemical reaction happen. So I'm just going to delete all that. The thing that they've locked is our final answer. Quite obnoxiously, they drew all the hydrogens. Did anything happen to a hydrogen? No. Okay, so if we look left to right, what's the only thing that appears to have changed? Okay, I've lost a pi bond. Where did the pi bonds go? Okay, a pi bond is really just 2 electrons. Those 2 electrons can now move somewhere. In a chemical reaction, we're going to move them to making a new bond. To make that new bond, we won't point to the bond. What we're going to do is point to the atom that we want to make the new bond with. So what we will do is say that those electrons are going to come out, and where are they going to make a bond? What carbon? If we look at our answer, what do we see as new in that structure? There's a new bond. I want to make the bond to that carbon. What else do I need to add? Good answer. Absolutely nothing. That's it. By taking those 2 electrons, what we have done is now moved them, okay, So if we erase this space, what we're now saying is we're going to place those 2 electrons in that space, which is what's making that bond. By making that bond, what happened to this carbon? It's now lost electrons. It should therefore be positively charged. All of that information is shown in the final answer. I don't have to dictate how that positive charges appears, because positive charges don't get moved, at least in chemistry. Electrons get moved. So just worry about moving the electrons. It's a single arrow from the pi bond out to the carbon. Did it have to be the pi bond that we drew? If I back out, did it have to be that pi bond? Caden, you're saying no. Why?
Because the molecule can just rotate.
Yes. Perfectly symmetric molecule, it does not matter which pi bond you use. That said, if you want to try and break SmartWork, go ahead and give it a shot. See if you can break it. Try and use one of the other pi bonds. They should absolutely accept it. And if they don't, that's where I can send them a nasty email being like, dude, you need to recode this. I know you wanted that one, but all of them are perfectly valid. Don't be shutting out choices. Did you just try and break it? Yeah, did it break?
No, it allowed it.
Okay. It should have allowed it, but that doesn't mean it did. Okay? And if you're looking at it being like, my question wasn't that, that's because it was a grouped question. What this homework was trying to do is make sure you had as much exposure as possible to all the individual mechanistic types. So you're getting a whole wide smattering of massive amounts of pooled questions. With that, we definitely have to be done.